Hello 8th graders, this video is about ELR 5.5, which is the next step in our unit. In the last lesson we talked about how there were patterns or trends on the periodic table as far as size goes, and you learned that protons make an atom shrink and adding a ring will make an atom grow. Well, this next step is, well, why does that matter? Why do we care how big an atom is? And it comes down to this idea called electronegativity. So let's jump right into it. At the top of your paper is the first note that we need to take down, and it is that atoms are reactive if they don't have a full valence ring. We've talked about this before. Another way to say it is that atoms want to have a full outer ring. That means that everything that's in the 8th column with the noble gases, those ones are all set. They're not going to react with any elements because they already have a full outer ring. However, everything else on the periodic table is kind of like a big playground full of bullies, and everyone's just trying to steal from each other. They all want more electrons to fill those outer rings. The thing is that some of them are better at getting what they want than others, and that's what this lesson's all about. So we have a word for how good an atom is at taking away electrons, or another way to think of it is how hungry for electrons it is, and that's called electronegativity. So on the table that's on my screen, and it's also on your paper, scientists have ranked each one of the elements with an electronegativity score. The higher the score, the more it is going to be likely to steal from another element. So if you'll notice, there's a pattern as you move across the periodic table. As you move from left to right, the number gets bigger, and as you move from top to bottom, the number gets smaller. Because of those two combining trends, the bottom left are the weaklings, and the top right are the most strong elements at stealing. Well, hopefully this sounds really familiar, because when we just learned about the size of an atom, you learned that the bottom left on the periodic table has the biggest in size, and the top right has the smallest in size, and that's directly related to the electronegativity. If you're thinking that's a coincidence, you'd be wrong. They are absolutely connected to each other. And here's how they're connected. Think about if you have a really small atom like fluorine or chlorine or oxygen up on the top right of the table. Think about what that means about how close they would be to any passing by atoms. So let's say that fluorine and rubidium, this big one down here, let's say they were passing by each other. Think about who might be closer to the electrons of the other atom's electrons. If everyone wants to steal, it's all about how close you are. So here's a better picture. Let's take fluorine and the biggest one on the table, francium. If they both came close to each other, francium has this one electron in its outer ring because it's in the first column, and fluorine, it really wants that electron. Francium would love to hang on to it too, but think about whose protons are closer to this electron, because it's the protons that are doing all the pulling. And fluorine is very much closer with its protons than francium is. And so that's why size is going to make a difference when it comes to stealing. So in other words, francium has a lot farther to hold on to its own electrons. It's reaching through all of these different rings. Even though it has a lot of protons, that outside electron is so far away that fluorine has an easy time just picking it off and running away with it. So here's a way to think about the whole periodic table. Down here on the bottom left of the table, we have got really big atoms, and they're not happy because they don't have a full outer ring. Think of it as if they have too much food, that they've got extra food. Then you've got these little scrawny elements on the top right, like chlorine and fluorine and oxygen, and they want extra. Well, because they're scrawny and scrappy, they're able to run in and steal the extra food. But here's the crazy thing that happens. Let's imagine this fluorine was able to swoop in and steal an electron. In this picture, it's the hamburger. All of a sudden, the metal that they stole it from, the big fat element, they all of a sudden became happy because they got a outer ring that's full. Well, when you take away electrons from an atom, it turns positive. So these atoms like to turn positive and get rid of their electrons, whereas the non-metal, the skinny small one, came in and stole an electron. Giving it an electron makes it positive. Well, when they were right next to each other in order to make that transaction, all of a sudden one turned positive and one turned negative, and opposites attract. And so this is what we call a compound. This is called an ionic compound because we made two ions that now stick to each other. And they're both happy because they got their electrons taken care of. So on your paper, there's a place where I need for you to think about summarizing these ideas. Number one, protons in the center of the atom are what attracts the electrons. Those are the things doing the pulling. So chlorine has more protons than fluorine, but fluorine is more electronegative. It's hungrier. I want you to answer why is that. Use your periodic table to think about that and think about the patterns. Number two, how is electronegativity and the size of an atom sort of like a hot dog champion? Now hear me out. If this is our hot dog eating champion and he is really, really skinny, how is it possible that this really skinny guy was able to eat so many hot dogs? Think about that analogy and answer 1 and 2 on your paper. If you're still watching, you are ready to work on the next section. So we have a few key points, things that we've talked about. Key point number 1. There is this thing called the octet rule. That rule says that elements want to be just like the noble gases, and they want a full valence shell. The word octet has oct in it, which of course means 8. Most atoms, except for the ones with the first ring, because the first ring only holds 2 electrons, most atoms want 8 in their outer ring. That's where this name comes from. It's the octet rule because they want a full outer ring. So think about this one. We've looked at sulfur before, and we've actually answered this question before. Look at sulfur. Sulfur has 6 in its outer ring at the moment. What are the 2 ways that sulfur could become obeying the octet rule? Pause this video and answer that question. If you're still watching, you're ready to see the answer. We can either get rid of these 6 electrons, or we can add 2 more to make the full outer ring. Now, the thing that sulfur is going to use to make that decision is its electronegativity. Since sulfur is a little bit further to the right on the periodic table than most elements, it's going to be better at stealing because it tends to be a little bit smaller relative to its protons, and so it's better at reaching out and stealing other atoms' electrons to become happy. Key point number 2. Whether an element gains or loses has to do with its electronegativity. So think about fluorine. Fluorine has 7 valence electrons, and if somebody had the strength to take away all 7, fluorine would become happy. But the thing is that there's nobody on the periodic table strong enough to do that. So the only way fluorine will ever obey the octet rule is by stealing. If you take something from the middle of the table, something in the neighborhood of 2, well, then it really depends on who's around. So if you take boron and put it with fluorine, fluorine's going to steal electrons. But if you took boron and put it with lithium, now boron's a little stronger and boron can do the stealing. So these ones in the middle are a little bit more flexible. They can behave either way. Key point number 3, if you have an atom that loses electrons, so an atom that's a metal, something over on the left-hand side of the table, the weaklings, when it loses an electron, we call it a cation, not a cation, a cation. And when an atom gains electrons, those are the bullies, the ones over on the right side, the little ones. Once it does that, we call that an anion. Now, the way I've always remembered this is that cats have paws, and therefore cations are positive. So now, before we get to the last key point, we have a couple of big decisions. On the left-hand side, we have our metals. Metals will most likely make which? I want you to circle one or the other, and therefore they would tend to have a which kind of a charge. Do the same thing for the non-metals over on the right side, and start this video again when you're ready to check. Now you're ready to check. Metals over on the left side, those are the fat kids. They're the big ones. And so they are not good at holding on to their electrons. That means that we're going to take away electrons, which is going to turn them positive. So cations, positive. Cations are what metals become. On the other side, non-metals are going to lose or gain their electrons, and therefore become negative, and those are anions. So guess what metals are likely to bond with? Metals and nonmetals like to stick to each other once they become cations and anions. So that's our last key point. And we call those things ionic compounds. A lot of compounds in the world are made out of these different things that have swapped electrons in order to make an octet rule. And then they stick to each other because they have become positive and negative. The next step for you is to do the practice side of your notes. You'll see that there are a bunch of boxes for the periodic table that are empty. Your job is to go through each row, starting with lithium, and make a little X inside of each box. Once you've made a little X, each little part of the 4 sides is going to get something different. So on the top, we're going to do protons, electrons, and neutrons, just like we've been practicing since the last unit. The left is going to get a Lewis diagram. The right, we're going to write in the symbol that it will make with a charge, and the bottom cation or anion. We're going to do the first one together. So let's think about lithium. On the top, lithium is going to have 3 protons, 3 electrons, and 4 neutrons. That's just old practice that we've been doing. For the Lewis diagram, because it's in column number 1, it's only going to get 1 valence electron. Those are the dots in the Lewis diagram. Because it has 1 valence electron, lithium is way more likely to lose its electron and become positive. So it's going to become lithium with a 1+. And because it's positive, we call those cations, and that's the last box. I need you to pause this video and work on the remaining boxes on your paper. The last part of this assignment is something called the ion love story. This is in Google Classroom. Basically, your job is to read the story that I've left for you in Google Classroom, all about ions. As you're reading through the story, think about how the ions in chemistry have been turned into people in the story. Your job is to either make the animations for this story or to write your own story using your own characters and your own setting. You can't just copy the one that you've read about in order to show me that you understand all of these different key points. So your 2 choices, either make animations or rewrite a new story. Whichever one you choose, you have to do all 4 key points. If you decide to do animations, I need to see all 4 of these key points in your pictures. If you choose to make a story, same thing. Got to have all 4 key points. Please let me know if you have questions. Ready, set, go.